a PhD student at CMU, working with David Woodruff. And he's done some really nice work on sketching streaming. So those of you who were here last week would have noticed a bunch of references to some of the work that he's done. But today he's going to talk about something completely different. He's going to talk about quadtrees, and it sounds like a very different, a nice different talk from the kinds of stuff we've been seeing so far. And a little bit about Rajesh is that he's just completing his PhD, and I just got to know that he'll be joining Google New York. And so he has actually received 2 Best Paper awards at this conference called PODS, which is one of the good conferences on principles of database systems. And so he's been doing a lot of interesting work in sketching, streaming, distributed algorithms. So without further ado, Rajesh, go ahead.
Thank you so much. I'm honored to have this invitation and to be here and see familiar faces. Familiar names. A lot of this is virtual, of course, and familiar faces. But so this is like you mentioned, it's going to be a little bit different than some of the other stuff that I've done, but there is going to be some strong relation to sketching and streaming ideas that I can go into later on, and we'll see at the end of the talk. But what I want to focus on for the most part is this very classic, what I want to call a meta algorithm or a algorithmic approach, which I'm going to call the quadtree in this talk, for solving this problem of high dimensional Earth mover distance. And so the algorithm quadtree, has been studied for a number of different things. It's, very classical, but what's new is an improved analysis, because we're going to show that for this problem of Earth mover distance, we can actually get a much better approximation factor than what was previously known. So of course, this is the joint work with Shi Chen, who's a professor at Columbia, Amit Levy, who just graduated with his PhD from Waterloo, and Eric Weingarten, who's now a postdoc at Stanford and also graduated last year from Columbia. So let's see. Yeah, okay, great. So the structure of this talk. So here's sort of my goal for this talk is I want to show you how basically all the classic chapters of your classic CLRS textbook are major players in this algorithmic problem. And so what we're going to do is we're going to go through all of these classic algorithmic paradigms to solving these types of problems and see how they compare and how we can think about problems from these paradigms. So by the end of the talk, I hope you reinvigorate your love for your algorithms textbook. So I'll start, before getting into that, I'll start with a chapter 0, just to tell you what the Earth mover distance problem is. So this entire talk will be about this computational task, which is called Earth mover distance. And if you're not familiar with it, what it is it's in some sense a meta metric. So it's a metric on a metric space. So if you have a metric space X with some distance dx, then the Earth mover distance is a similarity measure between 2 subsets of that metric space. So if I have 2 multisets, A, which is A1 up to AN, and B, which is B1 up to BN, they're multisets that can have duplicates, both of the same metric space X. And let me mention very briefly that for this entirety of this talk, all the sets will have the same size, little n here, although there are very natural generalizations where this isn't the case. So the Earth mover distance between 2 such sets, A and B, is defined in the following way. So in words, it's the cost of the minimum matching between the points in A and the points in B, perfect matching, where the cost is defined with respect to the underlying distance metric. So the way you would write that is this is the minimum over all bijections, pi, from the points in A to the points in B. So this is just a perfect matching. And then the cost of that matching here is the sum of the distance between each point AI and the point B pi I, which is matched to. So this is, in other words, it's a bipartite perfect matching problem between the points in A and the points in B. But the distances, it's a geometric matching problem because the distances are given by the distances in this underlying metric space X. And so what we're going to want to do is, and the purpose of this talk is to study algorithms which compute a good such matching for this Earth mover distance. So what is a good matching? Well, it's a matching n between the points in A and the points in B, such that the cost of that matching, which is the sum of the distances between each point AI and the point B m of I that it's matched to, is either exactly equal to the Earth mover distance, or not too much larger than the Earth mover distance. So let's say it's at most an alpha factor larger than the Earth mover distance for some approximation factor alpha. So we're not going to be only studying exact algorithms. For the most part, we'll be studying approximation algorithms, which return a matching, which is close to optimal, but not necessarily optimal. And so, by the way, feel free to, if anything is not clear, feel free to just interrupt in the middle of a slide, and I can answer questions. It's probably easier than monitoring the chat. But yeah, before I move on, I just want to make sure that the definition of the problem is makes sense to everyone, because it's the main problem we'll be studying in this talk. Okay, so fantastic. So what I want to do before I talk about how we solve this problem is I want to tell you, one of the principal motivations for solving high dimensional Earth mover distance. So in this talk, with the title of the work is high dimensional Earth mover distance. So what that means is that this metric space here will be high dimensional Euclidean space, or the high dimensional hypercube. So one reason why we would want to do that is by this very, very interesting to me application, and it's been a very impactful application in natural language processing. And this is called the word mover distance. It was introduced by this ICML paper of Kulzner, Solon, Kulkin, and Weinberger from 2015. And what they did is they used this idea of Earth mover distance as a notion of measuring similarity between documents or sentences. So they used it for as a natural language processing tool to tell whether or not two sentences are similar to each other or different from each other. And so what I want to do on 2 slides is basically tell you the very simple idea of how they do this. And so here we have 2 sentences. The first one is Obama speaks to the press in Chicago, and in Illinois, the president agreed with the media. And reading these 2 sentences, we can notice that semantically they mean essentially the same exact thing. They're trying to describe the same thing. On the other hand, if you just looked at a bag of words representation of these sentences share very few words in common. Their intersection is very small. So somehow we want to be able to describe the fact that these 2 sentences are very similar without just looking at the words individually and seeing what the intersection of words are. And what you could do is you could notice that there's some kind of matching here between the words in one sentence and the words in the other sentence, where Obama is really similar to the word president, because in 2015, Obama was the president. Speaks is similar to the word greeted. Chicago is a city in Illinois, and press is very similar to media. So there's some matching between these words, such that if we knew that these 2 words, which are different words, but if we knew that they were similar, we would be able to measure this with a sort of Earth mover distance type algorithm. And the key ingredient, the key technology, which allows us to do this, is this idea of word embeddings. So word embeddings are something that maybe some of you are familiar with, but the idea, and some examples are like word to vec or glove. But the idea is that you take every one of these words and you use these pre-trained word embeddings. I won't say how you train them because that's a whole subject in its own right, and I'm not an expert in that. And you use these word embeddings to map the words into very high dimensional vectors, or medium high dimensional vectors. And then now you have, and sort of the guarantee of this technology is that similar words semantically should get mapped to similar vectors that are close geometrically. So what the word mover distance says is just take your sentences, apply a word embedding to all the words, and then compute the Earth mover distance between the resulting vectors. And this should give you a measure of similarity. So this is sort of the picture from that paper of Kulzner, Kulkin, and Weinberger. We take each of these words, Obama speaks media in Illinois, and over here, president greets press in Chicago. We map them to some high dimensional vectors through a word to vec embedding. And then we see that Obama is very close to the vector president, speaks is close to greeted, and so on. So if we could compute the Earth mover distance between the points in one sentence and the points of the other, we'll see that this Earth mover distance is in fact rather small, because there's a matching where under the matched points, the distances are very close. So this is this high level idea, this application of word mover distance that allows us to measure similarity between sentences or documents by first mapping our words into high dimensional vectors and then applying an Earth mover distance algorithm with the resulting vectors. So this is one of the motivating reasons why we'll be thinking about high dimensional regime. But this is really just some motivation, and we won't really talk about this for the rest of the talk. We'll be focusing on algorithms, but this is something to keep in mind if you wanted to ask why would we be considering this regime. So now what I want to do is actually talk about how we would go about computing and matching or solving this Earth mover distance computation. And as I mentioned, we'll start with like this first classical chapter on how to on classical algorithms, which will be graph algorithms. And if we notice that this is really a bipartite matching problem, we have our blue points in one set and our red points in the other set, and we have distances which are given by the underlying metric. And what we want to do is compute the minimum cost bipartite matching. Now, if you're familiar with this problem, you may know that there's actually a classical algorithm, which is known as often called the Hungarian algorithm of Cullen Munkins and also Edmonds and Cart in the 1950s. And this is an algorithm, an exact algorithm, which will compute the minimum matching in order n cubed time between the sets. But it actually turns out, I learned this recently, that this algorithm has been known for quite a long time longer. Actually, I guess it was discovered in some of the unpublished notes of Jacobi from the 1850s, roughly the same exact n cubed Hungarian algorithm. So in some sense, there's this fundamental exact algorithm that's been known for quite a while. But on the other hand, it's a little bit slow for what we would like to go for. N cubed time is generally, in the data science regime, is rather slow. Now, we can actually improve on this a little bit by noticing this problem can actually be modeled as a min-cost flow problem. And then we can use these solvers, like this really fast min-cost flow solver of Lee and Sidford from 2014. And this will improve the runtime slightly to roughly n to the 2.5. And by the way, so far, this is sort of for general metrics. I've sort of avoided writing down the cost of like computing the distance between 2 points for this slide, because in any event, we already have very large dependency on n here. So I'm sort of ignoring the dependency on the dimension or the metric space. Unfortunately, if we want really fast algorithms, it's unlikely that we're going to get exact algorithms in better than n squared time. So if we want no approximation, exact computation, even for very simple metric spaces like Euclidean space, it turns out under there's some known conditional hardness results which says this is impossible. This is due to a paper of Rohatky in 2019. In particular, the conditional hardness is under orthogonal vectors conjecture. If you know what that is, if you don't, it's fine. It's just a conjecture which some people believe is true and would rule out a subquadratic algorithm. Okay, so we have some exact algorithms, but it's unlikely that we can do any better than n cubed time. So most of this talk, we're going to be focusing on approximations when we relax this notion of needing an exact algorithm. And before we go on, one might ask, like, what's another really simple way to approach this problem instead of these complicated Hungarian algorithm and min-cost flow solvers? Well, what if we just tried a greedy algorithm? So this will be another very standard approach that you could find in a CLRS textbook. And this would just say, look, you have these points over here and these points over here. For every point, just find the closest point to it and match it up. And then continuously do this over and over again until all the points are matched up. And then we could ask, how does this perform? Is this going to give us anything meaningful? Now, as you may guess, this actually isn't that fantastic an algorithm. And this was shown in a paper of Reingold and Tarjan from 81. They showed that even for the case of the line, so R1, this gives a very bad approximation. It gives a polynomial approximation, n to the 0.5849, something like this. But what I think is fascinating about this result is that notice that this isn't a big O here, this is a theta. So what they showed in this paper is that actually this is the approximation which is given by the greedy algorithm in Euclidean space. So for some reason, this crazy exponent is somehow fundamental. And I can't really tell you the importance of it because I don't have good intuition for it. But for some reason, there's some fundamental reason that this is the approximation factor for the greedy algorithm. But of course, this is a bad approximation, so we'd like to do a little bit better. And so what I will mention is that while this, for Euclidean space, you're not going to get a good approximation from the greedy algorithm, there are situations where greedy may be a good thing to do. And this is something I want to highlight because it's going to closely relate to the fundamental approach of quadtree type algorithms. And that's the fact that greedy, or so-called bottom-up greedy, is an optimal algorithm if you have a tree metric. So if your points are actually are vertices in a tree, and the distance is the shortest path metric in that tree, a greedy matching is actually going to be optimal. And so what do I mean by that? Well, I think the best way to see it is sort of a picture. So suppose we have some tree, and we have our blue points in one set and our red points in the other set, and we want to find a matching between the blue points and the red points, where the cost of this matching, the underlying metric, is the shortest path metric in this tree here. And so the bottom-up matching just says, take all the points at the bottom level and push them up one level down the tree. So just push them up one level up the tree, and then any points you can match up, greedily and arbitrarily match them up and remove them from the tree. And then you continue doing this, pushing the nodes up the tree, greedily matching up the ones you can, until all your points have been matched up. And then you get some matching with some cost. And it turns out that no matter how you arbitrarily decide to match the points up, this is going to be an optimal matching. And the proof is actually very simple. It's just a classic greedy algorithms proof, how you would show this. So it's an interesting exercise to see that. But this fact tells us that if we are able to somehow take our metric and put it into a tree, then maybe a very simple algorithm, which is just greedily matching points up, will give us something meaningful. So this is going to sort of hint at the idea of the quadtree. So now I want to move on to the main algorithmic section of divide and conquer strategies for solving this problem. And the reason this is the main section is because in some sense, the quadtree / tree embedding type approach is fundamentally a divide and conquer algorithm. And so now I'm really going to get into the meat of the problem and formalize things a little bit more. And so now, and for the rest of the talk, I want to actually just fix the metric space to be the d-dimensional hypercube with the Hamming or L1 norm on it. And so I want to say a little bit about why I'm doing that. So really what we care about is d-dimensional Euclidean space here. But for simplicity, we're just going to consider 0, 1 to the height of the Hamming cube with the L1 norm. And I'll mention that if you want to consider RD, there's actually very simple embeddings from the d-dimensional space down to the hypercube with a larger dimension, but we'll see soon that the dimension won't matter so much. And similarly, if you want to consider LP norms as, for P between, say, 1 and 2, you can embed down into a hypercube. So in some sense, without loss of generality, we can always study the Hamming cube for most cases we'd think about. So now, we're just, and remember this L1 distance is just the number of bits where two vectors disagree in the Hamming cube. So now I want to tell you what is known for this algorithm using this classic quadtree algorithm. And so as I've sort of mentioned informally a couple times, quadtree is this class of meta algorithms which go under this this general category of randomized tree embeddings. So this is a very old approach to algorithm problems, going back to this paper of Bartle 96 and also some even earlier works for a number of different algorithmic tasks. And specifically for the problem of Earth mover distance, Charikar and then later Indyk and Thaper in 2003 showed that it gives a linear time approximation for Earth mover distance. So here linear means if you have n points living in the Hamming cube, it's order nd time, and it gives you some matching, which is going to satisfy some good approximation for the Earth mover distance problem. And I want to mention this isn't the focus of this talk, but there are fast quadratic time algorithms which also give approximations, which are better approximations than these tree embeddings will give. So these methods like the Sinkhorn method, which will give better approximations than these tree embeddings, but they run in, say, n cubed or n cubed time d time. So they run in super quadratic time, but they give you slightly better approximations. Whereas here with these tree embeddings, we're thinking of like linear time or even near linear time algorithms. And one other thing I need to mention is that if you aren't working in high dimensions, if you're working in, say, the plane or in constant number of dimensions, there's results which give very good approximations, say constant approximations, using quadtree-based algorithms. So the key here is that we're studying the high-dimensional regime, where we're not going to be able to, so far as we know, get constant approximations for Earth mover distance with these types of approaches.
Rajesh, a very quick question about these, like the geometry approaches that you spoke about. Is the approximation ratio in those things also d-dependent, or is it only the running time?
Only the running time.
Oh,
yeah. So actually, we'll see in a moment that even here it's ultimately not going to be d-dependent. It will depend on n though, the approximation. But I want to say one other thing about this quadtree type approach, and I'm not going to be able to formalize why it's the case, But beyond these other methods, Quadtree has this other nice property that it's very lightweight and it's very flexible in some sense. And what this means is that you can actually use this algorithm, which is, we're only discussing offline algorithms right now, but you can actually turn it into a so-called sketching or streaming algorithm, where you could actually run the Quadtree algorithm while you see the points in the set A and B one at a time in some arbitrary order. So this will allow us to actually get streaming algorithms for this problem. And this is sort of another reason some variants of the Quadtree have this property that they can be run in the stream. The one I discussed is a little bit non-trivial to see that. Okay, so now I want to tell you what Quadtree is. I haven't told you really anything about what this approach is of tree embeddings. And so on this slide, this is just a very simple high-level idea of what this approach is. And really, it's a simple approach. It's nothing that complicated. The idea, you have this space, this hypercube of 0, 1 to the d. And so what we're going to do is we're going to recursively split up this space. So we'll cut it in half, and then we'll recursively cut it in half again and again and again. And every time we do this recursive splitting of the space, we get a recursion tree, just defined naturally from this recursive partitioning. So if we call this recursion tree T, then what we can do is we can take our points in our sets A and B, and we can naturally map them to vertices in this recursion tree based on what part of the partition they went to in the recursion. And so what this results in is that it results in taking our points and putting them into some tree, which is defined by this recursion. And then now we've somehow mapped our points from a hypercube into a tree. And what we're going to do is we're just going to do this greedy bottom-up matching on the tree that we saw earlier. And as we saw, like maybe for some reason doing this greedy matching would be a good thing to do in a tree.
So can I ask you a question quick? So usually when I think of a quadtree, even in D dimensions when dealing with geometry, often it's generalized to like a d-dimensional tree that's splitting on d axis is simultaneously into 2 to the d so subsets, and that would completely isolate each of the points and give you a tree of depth 1. Are you doing something more like you're dividing by 1 axis at a time?
Yeah, we're going to divide into hypercubes, but we'll in the simplest sense, we can sample 1 coordinate at a time and split 1 coordinate at a time. But you could do it like sampling multiple coordinates at a time. Like we're not going to do it in one step. But there's different trade-offs to this. And I actually thanks for bringing that up. I do want to say one thing about that. So like I mentioned, like I'm using this term quadtree in sort of a loose sense. So classically quadtree, there's the word quad in it, and that comes from the fact that I think this is classically studied in the plane, where you're splitting things up into 4 and then splitting them up into 4 more over and over again. And this is sort of I think where these algorithms originally came from. But because we wanted to sort of capture the fact that we're really studying the same algorithm, the same recursive algorithm of partitioning and then creating a tree. And so we use the term quadtree. And we're not the first ones to do this for high dimensional space, even though we're not going to be splitting necessarily into a branching of 4. Like as we'll see on the next slide, the branching will become bigger and bigger. But we do this just because really we want to be describing the same algorithm, and we don't want to be distinguishing between, I don't want to claim that we invented this algorithm. It's really the same idea.
So sure. So is the choice of what dimension you split, is that the same across the different branches of the tree, or is it independent like you would with a KD tree?
It can actually be either. It can actually be either, but I'll describe it as independent. I'm gonna hopefully answer your question on the next slide.
Okay, great.
For that. So I'm gonna now formalize. Okay, before I formalize this, I just want to give you a bit of intuition for those of you who haven't seen stuff like this of why this would be why this would make sense. And the idea is that if you have 2 points A and B in the hypercube, if these points were actually close together, then every time you divide up the hypercube, because these points were close, if you're randomly doing this division, close points are unlikely to get split by this division. So close points should stay together further in the tree. Therefore, they should be more likely to match together when you greedily match them up. On the other hand, if A and B were far apart, they're more likely to be split by such a random partition. And so they're less likely to be matched up. So this is sort of the intuition for why this kind of random recursive tree embedding it makes sense for this problem. And so before I formalize this a little more, I want to tell you what this algorithm was known to give. So previously this in high dimensions, d dimensions for n points, this Quadtree algorithm was known to produce a matching which gave a log n times the minimum of log n and log d approximation to the Earth mover distance problem. So this is the first part of this minimum was known by this paper of Andoni, Indyk, and Kraftgammer, and then the second part of the minimum was given by Backris, Dong, Indyk, Wasserstein, and Wagner in 2020. So really, if you want to think of like d and n as being polynomially related, like the number of points in the dimension, then this is kind of like a log squared n approximation. So the main result I want to tell you about now is a new analysis of the same algorithm, which basically removes one of these log n factors, going from log squared n to tilde O of log n. And so this tilde O of log n is hiding a log factor, log n factor. So this is the main result I want to tell you about now. And one more thing is that actually this approximation of log n is tight for this algorithm and this whole class of algorithms. So if you want to use this embedding into a quadtree and computing the distance from the quadtree, you're not going to get better than a log n approximation. So now I want to finally tell you a little bit more formally to answer Jeff's question about how we're doing this division. And so I'm going to divide this, as I promised, as a divide and conquer algorithm where we recursively partition and split up in a classic divide and conquer sense. So to define it, this will take input A and B, which are subsets of the hypercube. And I'm going to allow A and B to have different sizes because this is going to be a recursive procedure. So we may not always give inputs of the same size. And so it's going to take as input two subsets. And what it's going to do is it's going to match up some maximal pair of the subsets and then return some unmatched points, A prime, B prime. So for example, if A has more points than B, we're going to match up as many points in A as we can to B and then return some unmatched points A prime. Similarly, we would return some unmatched points B prime if B was bigger than A. And so the algorithm simply samples one coordinate at a time and splits the points based on the value of that coordinate. So what we're going to do is that if these sets aren't empty, we sample a coordinate I uniformly from the dimension, and then we create these four sets, A naught, A1, B naught, B1, where A naught is the subset of A with the ith coordinate of A equal to 0, and A1 is the subset of A with the ith coordinate of A equal to 1. So we're splitting based on the value of the ith coordinate into these, similarly to B. And then what we do is we just recurse on the ones and the zeros. So we recursively call the quadtree on A naught, B naught, and quadtree on A1, B1. And then this splits them up, and then they're going to match up in the two subtrees, match up as many as they can. But then there may be some unmatched points because, for example, there may be more A naughts than B naughts. So these two recursive calls will return some unmatched points, which are these A1 prime, B1 prime, and so on. And so then what we do is we just maximally match up. We have all these unmatched points. We match up as many of them as we can. And then any that are left over, we match them up arbitrarily. Any that are left over because one set was bigger than the other, we just returned it and set it up the tree. And this is the algorithm. And notice that if A and B, the input, were the same size, we never return anything unmatched because we're always matching up things as many as we can arbitrarily. So this is the entire Quadtree algorithm. I'll give a second to ask questions, but before I do that, I want to just show a picture of the algorithm because I think the algorithm is much more intuitive by picture. And so here's a picture of 4 points that we want to match together. And imagine these points are living in the hypercube. I'm not going to be able to illustrate that. And so we have a root of the tree, which contains all of the points. And so what we'll do is we'll sample a coordinate, and that splits the points in half into the points which had a 0 on that coordinate, the points which had a 1 on that coordinate. And then this creates two children of the root, those with the zeros, those with the ones. And then we send these points down here and these points over here. And then we just divide up again. We recursively do it where we split into the zeros and ones, and we keep splitting over and over again, making these cuts based on coordinates until everything is split up at the end. And then how do we get the matching? Well, then you start returning things up. So then you start pushing things up the tree and arbitrarily matching points up. And you keep pushing points up the tree and matching them up until you have a complete matching between the points and the same greedy matching. So this is actually the same as the algorithm I just described. It's just maybe a bit more intuitive. So this is actually the whole algorithm. Before I get into anything about the analysis, I want to pause and ask if there's any questions at all about what we're doing or the goal or the algorithm itself.
So you're not doing anything smart when matching, right? You're just completely arbitrarily matching and
Completely
hoping that
arbitrarily.
the random coordinate takes care of the
Yeah,
distance apart.
yeah, completely arbitrarily. Okay, cool. So I want to get into a little bit about talking about the analysis, and that'll be the majority of the rest of the talk on what we actually are doing here. So before I do that, I'm going to make a minor bait and switch. And this again will relate to Jeff's earlier question about how many levels. Are we doing this all in one shot or multiple? So what I just described to you samples one coordinate at a time. And so what that would result in is a tree with fan out 2. It would be a binary tree, and it would have depth d. So it turns out, and actually it actually won't matter ultimately, but it turns out from an analytic perspective, it's much easier to work with a so-called compressed quadtree. And what this is simply at the depth j of the tree, instead of sampling one coordinate, I'm going to sample 2 to the j coordinates, I1 up to I2 to the j, uniformly at random. And then instead of having just 2 children, I'm going to have 2 to the 2 to the j children, corresponding to all possible ways of fixing these coordinates. So what that means is that after log d levels in the tree, I'll have sampled d coordinates, which are all the coordinates at that point. So the depth of this new compressed quadtree is going to be only log d instead of d. And so really all I'm doing is I'm taking this depth d tree and I'm just taking sequences of 2 to the j levels and I'm compressing them into a single level. I'm just doing them all at once. So the picture is like this. At the first level, I sample 1 coordinate. I have 2 children. Then I sample 2 coordinates, and I have 4 children corresponding to all the way 0, 0, 1, 0, 0, 1 of like assigning 2 bits to 2 coordinates. Then I'll sample 4 coordinates and have a fan out of 8, and then so on all the way down the tree. And so, yeah, so this is just the simple modification. And with this modification in mind, I want to now describe this key ideal, which is the ideal which is going to run throughout the entire analysis. And the goal ideal dream scenario is that if I have 2 points A and B in the hypercube, and I'm going to use the notation A and B are in a vertex V in the tree, if those 2 points were mapped to that vertex when they went down the recursion tree. So here we have the root and some vertex V in the tree that's at depth J, and 2 points A and B, which were together in that vertex. They were still in this, it hadn't been split yet by that point. And the ideal is that if I have these 2 points, which were still together at depth J in this vertex V, then what we would like is we would like the distance between A and B to be no more than d over 2 to the j. And it's actually, and this is key point to keep in mind, because this is going to underlie the rest of the analysis. And it's actually not difficult to see, why is this the right thing? Well, note that if A and B were further than d over 2 to the j apart, at this level, we're sampling 2 to the j coordinates. So if A and B had more than d over 2 to the j coordinates that were different, then after sampling 2 to the j coordinates, we would have expected to see at least one coordinate where A and B are different. And then that would have split them up. So if A and B had more than d over 2 to the j coordinates which are different, we should have split them up by this point. So this is sort of the ideal, but as you can imagine, this is not going to always be the case. And in fact, in the worst case, we can have 2 points A and B, which are in the same vertex at depth J, but their distance is log n times d over 2 to the j. It's a log n factor larger than what we would like. And sort of the key takeaway, which I'm going to eventually tell you about, is that while this worst case can in fact happen in the tree, the main new idea of our result is that we're going to show that this can't happen too many times. Somehow, like the previous analysis said that this can always happen. What we're going to try to do is carefully say how many times can this actually happen, and that's going to be the main idea. And so to do this, we're going to introduce the 4th chapter, which is a classic algorithmic technique, an analytic technique for analyzing things like this. So we have some situation where we have some worst case thing that can happen, but we want to show that it doesn't happen all the time overall. So I'll just, I wonder, ask if anyone can guess what kind of analytic technique, maybe a chapter from CLRS, which describes this kind of approach.
Any recent algorithm students want to speak up?
Just a classic approach when you have some worst case thing, but you want to show that overall, over the whole course of the algorithm, it doesn't happen too many times.
Yeah, so if they can't get this, this is on you, Aditya.
Okay, what the punchline here is that we're going to be using an amortized analysis to show that overall the cost of the matching produced is better than the worst case cost that can happen at any given vertex. And so actually, we're going to play a little game and call it something slightly different, even though really it is an amortized analysis. We're going to call it an inspector analysis. And the reason we do this is that we're going to imagine that there's some like external omniscient inspector who's watching the execution of the algorithm and is going to start paying out some money to cover the cost of different things as the execution goes along. And so what we're going to do is we're going to show that the inspector is going to pay out enough money to cover the cost of the matching. And then we're just going to bound the inspector, the amount of money paid by the inspector instead. And we'll show that that's a much easier thing to control than the actual cost of the matching. So this is sort of a classic amortized analysis technique. And the key idea which allows us to improve over the prior analysis are two main ideas that I want to get as take-home messages. The first one is that these payments are going to be data dependent. They're going to depend on the actual point sets. Whereas, sort of prior results gave fixed edge weights to the edges in the tree, we're going to give data dependent edge weights in a sense. And secondly, the second new idea is they're going to capture some sort of average case notion of distortion in a tree embedding. So these are the two main ideas that I want new ideas. So to get across these insights, the first one, I need to define just a tiny bit of notation. And I promise it'll be very minor. So firstly, if I have some point A in the hypercube, I'm just going to define this notation Vj of A to be the vertex in the tree at depth j, which contains A. So remember, our points are getting mapped to this recursive tree, and they're going from some path to the root to some leaf. So it makes sense to talk about the jth vertex on that path, and this notation is going to denote that, the jth vertex on the path that contains A. And similarly, for any vertex in the tree, I can just write AV to be the subset of all the points in the big set A, which go through that vertex V, and I'll similarly define BV. And so now, with this notation in mind, I want to define this very simple notion of the center of mass. And so this is just the average of all the points which go through a vertex in the quadtree. So CV for a vertex V in the quadtree is just literally the average of all the points which map to that vertex in the quadtree. So it's the sum of all the points in AV union BV divided by the number of points, literally just the center of mass. And we're going to use this sort of average case notion to track the payments up the quadtree in a way to show that bad events can't occur too often. Okay, so now I can tell you what the actual payment scheme of the algorithm is and what we're going to keep track of. So the inspector, he knows the optimal matching. So he's going to look at the optimal matching, and he's going to look at every pair A, B, and the optimal matching. And he's going to pay some quantity for that. And that quantity is going to be, he's going to look down the tree and follow the pair A and B, and look at the first time that A and B split in the quadtree, and they go to different points. The first level where they split. And at that point, before that point, the inspector will not pay anything for that pair. But once we get to that point, the inspector is going to start paying cost for every single level below the point where they split. And the cost is going to be the distance from A to the center of mass of the vertex that A is contained in. So the picture is we keep going down the tree and we don't pay anything until we get to some vertex here where A and B split. Because here A goes into the left subtree and B goes into the right subtree. And when this happens, for the point A, we're going to suddenly start paying the distance from A to the center of mass here, A to the center of mass here, and then all the way down the tree, we'll pay the distance from A to the center of mass. And similarly, we'll pay the same cost for B. And so what we can show is that actually this payment scheme is enough to cover the true cost of the matching. So if we let M be this matching, which is produced by Quadtree, it turns out that if you sum the payments over all the points, the cost is at most 2 times the sum of all these payments. And I won't say the proof, but the proof is actually very simple. It's a very straightforward proof. The idea is that at the leaves, all the points are already on top of their centers of masses. So what you can do is you can move the points from center of mass to center of mass up the tree. And just by an application of triangle inequality, the distance from A to one center of mass plus the distance of A to the second center of mass is less than the distance between those centers of masses. So you can sort of move the points up the tree And notice that any points which needed to be matched, which are unmatched, must have been the results of some points being split earlier on in the tree. So sort of by two applications of triangle inequality, we can see that this is enough to cover the cost. And that's the main idea. So the key thing here is we actually need to bound this payment cost. This was the easy part. The hard part is to show that these payments aren't too much. And so what I want to do, let's see how much time we have. Okay, so what I want to do quickly is tell you how the worst case analysis worked, because I think it's gives some intuition for why this new idea of the average case notion is helpful. And so this worst case bound, which was inherent in the prior works, it did the following thing. So we want to analyze everything in expectation. So let's look at the expected distance between A and the center of mass at depth J. And as I mentioned, in the worst case, even the distance between A and the center of mass can be a log n factor larger than what we hoped it to be. Remember, we wanted it to be d over 2 to the j, but it could be log n times d over 2 to the j. And the way we prove that it's at most this is by this following simple fact. And this is a fact that this is just one fact that I want to highlight because it'll show up a little bit later. And it's that if I have any two points A and B that are at, say, distance alpha times d over 2 to the j, then the probability that they are still together at depth j is at most 1 over 2 to the alpha. And so given this fact, it's easy to prove this thing, because note, if you set alpha to be roughly order log n here, then no two points collide in depth j with probability 1 over poly n. So you can union bound over all n squared points to say no two points will be together if they're further than the distance log n times d over 2 to the j. In particular, the center of mass better be within distance log n times d over 2 to the j. Okay.
So the fact that the expected value has also the log n is because you are doing averaging over because it's the center of mass, right?
Yes, yeah.
Just to be sure.
So
Okay.
in the worst case, so this is always true, but in the worst case, you can have equality here, is the worry. And this fact, this bullet point here about this probability with alpha, it's not some difficult thing to prove. It's just a simple probability. You know, A and B, they have alpha d over 2 to the j points where they differ. So after sampling 2 to the j points, the probability that I haven't hit one yet is exactly 1 minus alpha over 2 to the j to the 2 to the j. This is order 2 to the negative order alpha. This is just a one line computation. So this fact says that points that become further apart, they become exponentially less likely to remain together. So this is like fact number 1. This says that far points should be split. So fact number 2 is I want the close points to not split early. So if I look at this pair A and B in the tree in the optimal matching, suppose the distance between A and B was actually d over 2 to the j. Now I would like them to split at this level j, but another bad thing that could happen is they could split early. So for any k, they could split k levels early. And so it's also not hard to show that the probability that A and B split by level j minus k, that is the probability that A and B split k levels earlier in the tree, higher up in the tree, well, sort of just by a Markov inequality, this is at most 1 over 2 to the k. This is a similar computation. They have that many fewer coordinates that are different, so that's the probability that you'll find one of those coordinates. And so putting these two facts together, if A and B split k levels early, they'll pay a 2 to the k factor more because the distance to the center of mass can be that much further. And so now this is actually all you need to know to recover the earlier bounds which are given for Quadtree. And I'll just do that on this one slide because it's not too difficult. So if I have this pair A and B with distance A minus B is d over 2 to the j, then what is the expected payment for this point A? Well, what I'm going to do is I'm going to sum over all the levels where A and B could have split early in the tree. And remember, the probability that they split k levels early is at most 1 over 2 to the k. But if they do split early, then I pay the distance from A to the center of mass k levels higher than where they should have split. It turns out that the lower levels don't contribute much, so you can ignore them. So just plugging in what we know, the worst case bound is log n times d over 2 to the depth, which is here j minus k. These 2 to the k, 1 over 2 to the k cancel. So we get log n times the actual distance, because remember d over 2 to the j was the actual distance between A and B. But now the depth of the tree is log d, so we're summing this log d times, so we get log n times log d times the actual distance. And so this says that the payment in expectation is the most log n times log d times the actual distance. And summing this over all the points, this says the overall approximation is at most log n times log d times the sum of all points, which is log d times the optimal cost. So what this says is that what we just done on a couple slides is completely prove the earlier approximation, which was known for Quadtree. But what I want to do now, and we spent a lot of time doing that, but it turns out that now, like, it's actually very easy to say what the new idea is in just a couple of pictorial slides. And so what happened here? What was the difficulty? So intuitively, we had this bad event, which is that pairs A and B, which we wanted them to split at level J, they could have split earlier, higher up in the tree by some bad event. In fact, they had log D chances to split earlier because there's log D levels in the tree. And what we said is that every chance they had to split early, we're going to pay the worst case cost. Like, we're saying every single level, in the worst case, the distance from A to the center of mass is log n factor larger than it should be. And so as a result, we got a log n factor times a log D factor. So like I said earlier, sort of this the main simple new idea is that we're going to show that you have these log D chances to split early. We're going to show that only on a small subset, a poly log n subset of these log D levels, can you actually pay this worst case factor. So it can't be the case that at every single level up the tree, the distance from this A to the center of mass is a log n factor larger than it should be. It just can't happen. That's what we're going to show. And so in particular, we're going to prove the following fact. The expected distance from A to the center of mass, it can still be log n times d over 2 to the j. But like I just said, we're going to show this only happens for at most poly log n levels in the tree. So we're going to fix a point A, and we're going to look at all the distances from A to the center of mass. And we're going to say that this bad event, where it's much larger than it should be, can only happen, say, log n times or log squared times. And so now I'm just going to prove this whole thing in a picture, in sort of an example picture. And the example is going to look like this. So suppose I have some vertex V with a depth J. We're at depth J, and we have some point A, which is this circle here represents all the points which are contained in this vertex. And this black point here is the center of mass. So what is the bad event? The bad event is that the distance from A to CV, we would like it to be d over 2 to the j, but suppose it's larger than it should be. So for example, suppose that it's log square root n factor larger. This is like 1/2 log n. Well, for this to happen, well, there must have been some point P, which was also distance log root n times d over 2 to the j. Because if the center of mass is that far, then there must be some point that actually was that far as well. So there's some point P, which is a log root n factor larger than it should have been, and it collided with A. Now remember, we have this fact that if A minus P is the distance is alpha over d over 2 to the j, then the probability that they actually collided was 1 over 2 to the alpha. It was exponential in that extra distance. In particular, that means that if this point A and P collided and they were log root n far apart, then the probability that this actually happened was very small. It was only 1 over root n. So in particular, it says that if I had such a point that actually did show up, the probability they showed up was 1 over root n. So if such a point did show up, there must have been many other points which were at the same distance which didn't make it. So in particular, it must have had root n points in expectation which were at the same distance of log root n over d over 2 to the j, which weren't captured in the set. Because otherwise, if I didn't have this many points, the probability that every one of them comes in is 1 over root n. If I had fewer than root n points, I don't expect to see any. So in expectation, if the center of mass is far, there must have been root n points which were far in the actual space. And so now what we're going to do is we're going to use this fact, and we're going to walk a couple levels up the tree until these points, these root n far points, now become close points. So let's go to a new vertex U, which is log n levels up the tree. I'm just going to walk a couple levels up the tree so that in expectation, all these root n far points are now close points. So at this new vertex, only a couple levels up the tree, log n levels up the tree, all these points should now basically be contained in the same vertex that A is contained in. And moreover, these points are now within, the distance was log n times d over 2 to the j, but because we've gone log n levels up, these are now close points now. They're no longer far. So what could happen now? What if a bad event happened again? I know I have at least root n points that are close. So if the center of mass was still far away, So if the center of mass in particular was, say, log square root n times d over the depth of the new vertex, depth of u, then because I have root n points which are close, there needs to be root n points which are far. So I need to have a bunch of points which are actually far away to pull the root n close points, because remember the center of mass is an average. And again, each of these root n close points, which needed to collide in the vertex, of course, maybe you're seeing the pattern here. Each of them collided with very small probability, with 1 over root n probability. So there must have been n points which were at that same distance for there to be root n points that survive after 1 over probability 1 over root n. And so, like, you can keep playing this game and saying every time this happens, you must have had many, many more points which are just outside. But notice that at this point, the game has ended because we've run out of points. Because every time we had a log n factor bigger, we actually needed to increase by sort of a double exponential rate the number of points that were nearby. So at this point, a bad event can't happen again because now we've captured all the points that exist. And so this is actually basically the entire proof, is that showing that every time some sort of bad event happens, the number of points around you is increasing at a doubly exponential rate in the degree of badness of this distance to the center of mass. So slightly more formally, we prove this one lemma. This is basically just the same thing we just showed on the prior slide. If you look at the ball of radius r around any point A, this is the set of points in A and B, A, U, and B, which are at radius r around A. If it happens, the distance in expectation from A to the center of mass at some vertex V at depth J is an alpha factor larger than it should be. This is an alpha factor bad. Then the number of points in a ball, an alpha factor larger, is growing by 2 to the alpha factor larger than the points that were at the actual distance. So every time the center of mass is bad by an alpha factor, then the ball number of points around you needs to grow by a 2 to the alpha factor. And then you do some bucketing, and this shows you that overall you can only have poly log n bad levels where this factor alpha here is super constant. And this is basically the end of the proof. Altogether, this shows that the payment, the expected cost of the payment is tilde log n times the actual distance, and then you sum this over all the points, and this says that the overall cost is a tilde of log n approximation of the actual Earth mover distance. So this is the main new idea, pretty informally, but I think it really captures the main idea of what the analysis in the paper does. So this is the end of the analytic, mathy part of the talk, and I'm almost done. The hour is almost over. So before I go on to some problems, I want to just see if anyone has any questions about this at all.
So are you going to say some more, or I have a few questions. So, do you think this log n factor that you get, or maybe I missed if there are other things hiding in the analysis, but is inside the tilde, do you think that's something that arises from your proof structure, or it seems like it's actually is necessary, and there might be actually a stronger lower bound, that the lower bound might be log n, so log n?
Yeah, so I'll say two things. I'll say that for this analytic strategy, if you sort of look at it, I think you pay at least 1 log n. So our analysis, we have 2 log n's. One comes from sort of like this doubly exponential thing, and the other comes from this fact that we're being a little loose here. When we go up log n levels, and we say all those levels were bad in between. I think with a little bit more work, you could remove that log n. You just need to do the bucketing a little bit more carefully. But there is sort of 1 log n factor, which comes just by imagining just actually putting it the factor as large as you possibly could, and growing doubly exponentially at that point. But that would say that you could prove that the inspector cost, this cost payment scheme, pays an extra log n factor. But then if you actually try to set this up and look at what the matching would pay, it actually wouldn't pay this factor. So here there's a discrepancy between what the Quadtree is actually producing and this analytic strategy of the inspector. So for this strategy of tracking the center of mass, I think you need to pay at least 1 log n. but I don't think there's any reason why fundamentally this should be inherent in the algorithm. And the natural lower bound is only a log n lower bound for this tree embeddings.
Yeah, thanks.
Of course. So I just want to say one very brief slide about streaming, because I did hint at this earlier. And so the streaming problem is, very similar to the offline problem. We have these, we're trying to compute the same thing, but we're going to see the points in the set A and B one at a time, these points in the hypercube, and we're going to see them in some arbitrary order. And our goal is to compute the approximation in as small space as possible. And something that I didn't tell you was that this earlier algorithm that gives a log squared n approximation, it can actually be formulated by giving weights to the edges of the tree and sort of doing this thing called an L1 embedding, where you embed the tree metric, earth mover distance over the tree metric, into L1 metric. And it turns out L1 distance can actually be sketched and maintained in the stream very, very efficiently. Unfortunately, when you look at this actual cost and you don't do this embedding, and you want this log n approximation, it's no longer clear whether you can embed it into L1. So the analysis we described is not an L1 embedding. So it turns out it's a bit harder to actually translate this new analysis into a streaming algorithm. But what we are able to do is give something that captures the same improved, like the best known new approximation of tilde log n, if you're allowed 2 passes over the data. So if you get to see the data twice, we can actually simulate this exact algorithm that I just described to you using the same approximation, using a very small number of bits, polylog n, polylog d. And additionally, using quite a bit more work, if we have this nice property that the sets A and B, they don't overlap too much. So imagine that the ratio from the intersection to the union isn't too close to 1. Like these sets aren't exactly right on top of each other. Then we can actually do this in one pass with a classical streaming algorithm, getting the same approximation using polynomial in this epsilon, which is how close you are to being on top of each other, and so on. But unfortunately, the thing that keeps us from solving all these open problems in the sublinear.info, which has been this long open problem in a lot of different regimes to try to sketch and stream earth mover distance, is that we still have this this constraint. Like this, that for some reason this doesn't handle the case where you throw a ton of points in A and B on top of each other. They don't cancel out in this analysis. So one open problem is just like, can we remove this assumption? Can we get a streaming algorithm that gets this new approximation that we get from our new analysis with a small amount of space, like not like much sublinear in n, there's a lot of points n, in one pass without any such assumption. And then like one final open problem that I'll mention now that we're at the end is that there's actually a whole class of metrics that capture the earth mover distance as a subcase. And these are called the Wasserstein P Metrics. And in general, these are defined on probability distributions. What we described here was the earth mover distance on a discrete distribution on endpoints. But as I mentioned, it doesn't need to be a discrete distribution. It can be continuous, but you would have weights and so on. And these Wasserstein metrics can be defined with many other powers. Instead of just summing up the distances, you can sum up the pth power of the distances. So a good analogy is if you know the clustering literature, there's this k-means clustering, and there's also k-medians clustering. And so the question is, do you sum up the distances from the points to the center, or do you sum up the squares of the distances from the points to the center? This is sort of a similar analogy here, where the Wasserstein 2 distance, for example, is the sum of squared distances between the points that they're matched to. And it turns out that this Wasserstein 2 is very important in practice for generative adversarial networks and a number of other, a lot of people prefer Wasserstein 2 for a number of different reasons. Unfortunately, the algorithmic properties of Wasserstein 2 are much poorer than the algorithmic properties of the earth mover distance, which is the Wasserstein 1. And in fact, these quadtree-like constructions will not work for Wasserstein 2 for a number of reasons, which I'm happy to explain after the talk. So we really don't have any efficient sketching or streaming algorithms for the Wasserstein 2 metric or anything like this very fast approximation, unfortunately. So this is I think a very interesting open question to try to see if any of these randomized tree embedding approaches could be somehow modified to give us something for Wasserstein 2. But so far, we don't know how to do that. And yeah, so that's everything I had. So thank you so much for coming and for your attention. And this is the last page of CLRS. So just to wrap up. So thank you so much. and I'll take any questions.
Yeah, thanks a lot. Yeah, actually, I mean, I will wait until if somebody has questions, go ahead. But if not, I wanted to ask a little bit about the Wasserstein 2 distance that you mentioned at the end, like what kinds of things fail and so on. But before that, does anyone have questions? Okay, yeah, I guess maybe then you can talk about that.
Yeah, so it's actually not too hard with the context of this talk to see why this would fail. And
correct. Yeah. So this failing, I agree. But you were saying that really methods like this don't quite work.
Sorry. I don't want to claim like some general lower bound that no tree embedding doesn't work. What I want to claim is that like you think about this for a little bit and it seems unlikely. And also I know a lot of very smart people other than outside researchers have worked on this, and as far like at least as far as I'm aware, and it seems elusive so far. And I do know actually we do have some partial results for lower bounds for streaming. Oh yeah, actually there I had some slides on implementation. So actually it's a very simple algorithm, and so we did actually implement it, and we showed that this inspector cost is very useful for a nearest neighbor search. So one reason I mentioned this application, sorry, I'm answering a question in the chat very quickly.
Yeah.
This application of word mover distance, it's most useful when you're thinking about document similarity, where you have a bunch of documents and you get one and you want to see how similar, which one is the most similar. So what you do is you compute this earth mover distance, this word mover distance between each one, and then you pick out the one with the smallest. And really, what you care about is how it performs in like top K recall. What's the probability that your algorithm finds the top K, among the top K closest, the true closest document under some notion of what the true closest document is. So we actually have some results for this that we're planning to send out. But what I would say that probably the best thing to look at is there's this paper that I cited, Dong, Ilya Rasenstein, Pyotr Indyk. Actually, let me find the name. It's called yeah. Okay, so the paper is called. Let me just send it in the chat. So this paper here, I just sent it in the chat. It's the paper I cited that gets 1/2 of this min. So it's mainly an experimental paper at ICML 2020. So that they have some very nice implementations that are open source on GitHub. Their code is much nicer than the code I wrote. So I recommend if you want to play with implementation, I recommend looking at that, because they implement this algorithm and a number of other algorithms like the greedy algorithm, and also and they show that this and one thing I'll note about that paper is what I described in this talk is what they refer to as flow tree, meaning the difference between flow tree and quadtree being that flow tree looks at the distances in the original metric, which is what we did here. And Quadtree does this actual tree embedding thing into L1, which I didn't actually discuss in this talk. I used Quadtree to refer to both things simultaneously because, like I mentioned, I wanted to use this term Quadtree broadly to capture a huge class of algorithms and not really distinguish between different implementations. But there is an important distinction there that's talked about in that paper. But yeah, so for the Wasserstein metric. I can't claim that there's no tree embedding that would work here, but there are no lower bounds for embedding into L1. They're not as strong as you would like them to be. Like one could imagine that you could get much stronger lower bounds.
Right.
Yeah. So probably there's a much bigger penalty for missing on the things that aren't close, right? And that's what the tree embedding does not do a good job of capturing.
Yeah. Yeah, somehow like you make one mistake in the tree embedding and you split things early and you pay a huge cost for that. Like you don't get there's no notion of like repetition. Like somehow like you want to like repeat things to and like take an average to like even out the cost, these dramatic costs of like one outlier messing up the whole thing. But somehow the issue with tree embeddings is that there's no notion of multiple if that makes sense. Like once you split early in the tree, that distance is fixed. Like it doesn't matter what happens later on. You're only as close as the earliest level where you split.
Yeah.
And for some reason that causes big issues when you have like these huge outlier distances that distort the cost.
So there's some stuff in geometry that gets stuff to work with L2 variants using trees, but they often do these like randomly shifted trees and then somehow combine the results of a few of these. Is it make sense or feasible to have multiple trees at the same time in this, or having multiple randomly shifted grids is not going to work within these frameworks? So
for this analysis, I don't think it will work, but I would say I'm actually really interested to take a look at some of those results, because that's something that we thought about. A couple what happens if you okay? So here's a natural algorithm. What if you just repeat this tree multiple times? You send all the vertices to multiple different leaves, and then you could do a greedy bottom-up thing where you do greedy simultaneously and all of them at the same time, and then you match it whenever any point intersects, you match them up and remove them from all the trees. So it's like greedy simultaneously over multiple repetitions.
Yeah.
This seems like a natural. I don't know how to analyze this. We thought about it for a bit.
Yeah. So like the stuff for so like minimum spanning tree, and so in the plane, for instance, right? This is how these algorithms work. But this has worked. So like so I think Sharath Raghavendra has some work looking at these tree decompositions. I think his work has randomly shifted kind of quad trees underlying a lot of this stuff. But I think it's mostly low dimensional geometry. I might be missing some of that.
No, I'll definitely take a look, because I had thought about this and we played with it a little bit, but like we didn't really know how to analyze it. It seems hard to sort of keep track of things, because one nice thing is that you actually have a metric when you embed it to one tree, but when you have multiple trees, like minimum distance over multiple trees is not a metric space anymore. So you lose nice things like triangle inequality, and I'm actually curious, like just even from a practical perspective, how this would perform for like Wasserstein 2, for instance, because maybe it would be glaringly bad, but it seems like a natural thing to do.
Yeah. So this is also used a lot in I know some work in high dimensional nearest neighbor search for joins. So we're trying in the database world.
Yeah.
Where they're trying to find kind of all the things which are close, which is a similar problem. They'll use a small number, like 2 or 3 of these randomly shifted quad trees, and a small number of those gets around and this is practical stuff, right? But it gets around a lot of the horrible kind of splits that you get in practice if you're only using one tree, of things that are very far apart, even though they're right next to each other. But if you have a few random shifts, those become much more rare.
That makes a lot of sense, actually. Yeah, we've been interested in the practical aspects of this as well. So I think that's actually a really good pointer. We'll look into that, because I think there's definitely a lot of different room to play here, but I think we're just only starting to understand how these things work.
Yeah.
At least personally, I know people have been studying them for a long time. I will say that we have a follow-up so you mentioned minimum spanning tree. So you could ask the same problem in high dimensions, and it turns out the same algorithm actually works. It's the same. You do sort of the natural thing. You push things up and you make an MST greedily, arbitrarily on everything, and then you push one vertex up. Using a similar analysis, we have a follow-up that shows that you get an improved approximation that was known for MST using this new amortized type analysis for high dimensional MST. And one nice thing about this is that you actually do get a one-pass streaming algorithm using similar techniques with no criteria here. Actually, I didn't say this, but another way of looking at this assumption about the sets being not too overlapping is that in some sense, we're also giving an additive error. Like there's some additive error here. And that additive error is bad if the sets are too far on top of each other, because then they're too close together. But for MST, we don't get this additive error. We're still trying to figure out whether this additive error is necessary.
Yeah. Yeah. So I want to ask you one more question, unless.
Can I intersect the question?
Yeah.
So I have two questions. I think they're probably both a bit sort of out of the box a little bit. So you mentioned that this tree metric, that if you embed everything into a tree metric, and then this framework will work. What if I have a scenario where, I have a few violations to this tree metric, meaning that I kind of look at the tree, but I allow a very small percentage of them to be tree-like, but not exactly tree. So for example, like I have a few maybe leaf nodes connected with one another. So all of a sudden, I throw an edge to my tree, right? So in some sense that, it's sort of like not a perfect tree, but it's almost. Is there anything you can say about that?
Right, let me think. So it's okay. So in this analytic framework, it depends on, like, you have to. It's no longer, you have to make sure that there's a clear definition of what the greedy matching is, because if you have an actual tree, then the greedy matching is well defined. You take the things at the lowest depth, like depth is well defined. So I suppose you could have like a DAG, and then you could have maybe some extra edges, so you'd have some well-defined greedy matching. But then I guess the issue is that you have some choices, right? Like you maybe not have one parent, you could have two parents if it's no longer a tree. So if this is the case, I think it might be very difficult to argue about what happens, because somehow the algorithm is like you have to choose, you have to decide what the algorithm is going to do now, because the algorithm has to make some choices on where to move points. Because the nice thing about a tree is that there's no choices to make. Like you always just go up. So okay, so one thing I can imagine being interesting to look at is doing like a random choice or even an arbitrary choice. Probably a random choice might be better, but I'm not sure. I'm not sure. I haven't thought about this much, but I imagine that there could be some advantage to doing this. Maybe even the one thing that strikes me as possible is that there might be some advantage to doing this for the Wasserstein 2. Because as we saw, like somehow like this one split could cause you a lot of issues. Maybe if you gave it some chances to come back with some extra edges, like some bounded hypertree width like property, perhaps then you could get better algorithms for Wasserstein 2. Of course, like the algorithm I described is like it's so simple because it allows us to give an analysis for it. The difficulty is that it becomes surprisingly difficult to give tight analysis for these algorithms as soon as you leave the very simple space of an actual tree. And sort of like the reason is that like a lot of these earlier analysis, and even this analysis in some respect, although we don't say it, but like in some respect we do really rely on this fundamental fact, which is that the greedy algorithm is optimal for a tree metric. So what that means is that once you don't care about what earth mover distance is a complicated thing. Like you're optimizing over all possible exponentially many matchings between two pairs of points. The nice thing is that once you go to a tree, you forget about this crazy optimization problem, because you just know that the greedy is the optimal one. You don't care. You don't need to look at different matchings. So really, the only step that you need to analyze is the step that takes the points and puts them into a tree. You just need to analyze the distortion of the metric embedding, which sends points from some metric into your tree. Because once you get into the tree, you can forget about earth mover distance, because that's taken care of by the greedy. But once you leave that space of a tree, now you need to think about this earth mover distance, this optimization problem over many different possible matchings, and these the type of stuff that goes into the Hungarian algorithm, where you think about augmenting paths and the issue of well, what happens if I match this guy up with the wrong thing, and now this guy has to get matched to something else, and these are the kinds of it becomes quickly complicated. And so the nice thing is, by working with trees, you get to kind of forget about all these issues with matchings, just by using the fact that greedy is optimal. So I guess I would say that I think these are really these could definitely be really good ideas and really powerful techniques, but I think they're a lot harder to analyze theoretically, because I don't think we have good tools as far as I know, to analyze them once you lose this nice tree structure.
Yeah, I mean, I guess my motivation of asking that question is thinking about sort of the more general optimal transport type questions, right? Instead of one mass to go to one mass, which is in the case of greedy algorithms, I could have one mass goes to, 50% goes to here, 50% goes to there, right? So it's sort of like a sort of distribution in terms of matching. And the moment I go there, I can no longer kind of describe the matching through this tree structure. At least that's my understanding, is that the moment you can split like a matching to go from, from one single mass to say some percentage to go one place, some percentage to go to another place. And that kind of break this tree metric formulation, I guess.
So let me say one thing about that, because I didn't describe this in this talk, but actually the same exact algorithm solves the problem that you're describing, where you have weights on all the points and you want to match like some fraction of one to some fraction of the other. But like the overall weights are equal, like the total number of weights in A and the total. So you have you have a probability distribution over A and a probability distribution over B, and you want to match up. So actually the same exact algorithm works and the same exact analysis works. And what the algorithm does is like, you send all your points to the bottom, and then you push up the points, and then you match as much probability mass here as you can here, and then you send the excess mass up the tree in whatever points that you do it arbitrarily. So the actual same algorithm works. And one way, if you want to see one reason why the same analysis works, is you can imagine, like, suppose that your probability distribution, like you could write it with like say log n bits. Like the number, like you like the probability mass had some common denominator that's like log n bits. And so what you could imagine doing is is putting it into this framework by duplicating points. So like if I have something that has probability, if like the granularity is delta, like delta is 1 over poly n, then I could have 1 over delta distinct points in both of the sets, and I could just duplicate one point the number of times that its probability mass corresponds to. And then this actually takes this problem of optimal transport and it puts it into this discrete variant here. And if you notice that you wouldn't actually ever want to do it like this, because now you've blown up the number of points polynomially for the runtime. But notice that the analysis actually goes through just as well, because you have a log, and so long as you've done this a polynomial, as long as the granularity is polynomial, like the bit complexity is log n, then the same approximation, you get the same log n approximation doing this algorithm. So actually the same analysis goes through, although the algorithm you would actually want to do is like really matching up the probability flows. So yeah, I guess the answer is you wouldn't need to do anything other than a tree metric.
Okay, so to summarize that, if I have this sort of probabilistic matching, right, kind of almost like many-to-many kind of matching, you are saying that if I somehow duplicate my labels and kind of distribute the mass into actually unique sort of units, and I can just pretty much apply the same framework through the sort of greedy tree matching, except that, if I have one object has matched to object 2 and 3, I would just have duplicated this object twice. Yeah. And analysis goes through because of, it's still a probability distribution. So somehow the math will give me the same approximation.
Yeah, so actually the n in the approximation, the log n, I didn't mention it here, but you can show that really what that n is, the approximation doesn't depend on the total number of duplicate points, the size of the sets. It depends on the number of unique points. So like if I do this duplication, it doesn't actually change the approximation. And the reason is that really like this log n comes from this union bound that we saw, where you saw this worst case event, I need to union bound over things. But points that are duplicated, they always go to the same, like at one point you duplicate, the same thing is going to go to the same place in the tree because it's the same point. So this actually doesn't affect the approximation at all. And if you're interested in like a very simple explanation of how this works in the probability distribution land, that archive paper that I sent in the chat, it describes the same algorithm here that we're describing here, but it describes it in the general probability distribution sense. I chose not to do that here for simplicity for people who hadn't seen Earth mover distance, because it's a bit of a mouthful to even explain the problem. But yeah, there's actually there's no loss of generality when going to that setting.
Cool, thanks. Jeff, you want to ask your question? Then I have another question.
Sure. Yeah. So So I want to ask, so by doing this recursive splitting, and I like to, you're actually defining a one-dimensional order over the points if you split them one time at a time. And I mean, one of the reasons this came up is that this was kind of the core step in some actual empirical algorithm I worked on about 8 years ago, and we found using a Z in 2D, using a Z order over the points. And then using the one-dimensional structure actually made so things faster. Now it wasn't L1 Earth removes distance; it was a different matching problem, but it was still a matching. And we found you lost a little bit of error by doing Earth removes distance instead of the distance arising by the Quadtree, because you're enforcing and ordering over things. But that seemed not to be where you're losing error. And it was, but there was still randomness, which helped. So, okay, so I'm asking this in the context of, like, at the beginning of the talk, you mentioned in one dimensions, there was this polynomial approximation bound, which was tight, right? So
for the greedy algorithm.
But you're effectively doing a greedy algorithm once you've defined a one-dimensional order, but there's it's not the full greedy algorithm, it's somehow worse, right? Because I'm not allowed to match certain things which are next to each other. I can only match them if they're close in the tree structure. So the question is, like, what's happening that's somehow getting you around this lower bound for one dimension?
Definitely. So I think the easy answer to that is that we had the randomness, the random shifted grid in the Quadtree. The fact that we're not deterministically doing it. Like, so if we randomly choose a coordinate, another way of thinking of it is like the classical Quadtree type algorithms that maybe are more typical, where you have like a grid. We're doing like a random shift to that grid. Right. And if you don't do the random shift, then none of this works.
Okay.
And so it's really easy. So if you look at this paper of Reingold and Tarjan, there's a very nice diagram which actually shows the construction. It's a very neat construction. And what it is it's just like a line, and you have 3 points that are close together. So you have 4 points. And the issue, and you could either match one to this one and this one to this one. So you have 4 points. You could match the outer ones, or you can match the middle ones together. But then the 2 on the side would have to go all the way around, right? But because these 4 points are all the same distance from each other, a greedy algorithm doesn't know the distance between matching this, and it's going to match one thing first. But everything's there's three different things you can match. You can match this, or this.
Right.
So if it's sort of a worst case greedy, because the greedy can do whatever it wants among the arbitrary choices. So it can pick to do the middle one first. But now it does the middle one, it has to match the far ends to each other. So it pays a bad approximation there. And then so what the construction is it takes that simple thing and it recursively makes like sort of a fractal, like it does it recursively, and it does that thing like several times over and over again. And then every time, like at the end, like you're picking something that has to go all the way over to the other side. So whereas like in that situation, there is a greedy algorithm which gives you the optimal solution. But there is also a greedy algorithm that's very bad, because there's many greedy algorithms. It depends on which one you choose first. Right. So the point is there that if you just say greedy without any arbitrary choice, it would be very bad. But if you look at that same example and say, let's randomly choose, let's inject some randomness into where we choose, or where we split up the choice, then this problem would go away. Because if you look at the construction, the second you choose one part right, you choose the right thing, the construction stops. Like you always get everything right from there on. So it's only when you have this cascading effect because you always choose the wrong thing.
Yeah, great. So thanks. So thanks for the talk. So I'm going to have to leave also.
Yeah, thank you so much. It's great to meet you.
Yeah.
So Rajesh, I just have a really quick question. Sorry,
Sure.
I kind of I know it's a little bit over time, hopefully.
No, I have nowhere to be.
Okay, I just had a pretty naive question. With this analysis, I think it all looks very pretty in high dimensions too. So does it have a practical consequence even in 2D with this analysis? For example, like your intuitive example is indeed showing 2D in your slides, right? So does it help? And if it does, to what degree does it help in computing Earth mover distance in 2D?
Right. So this algorithm is the algorithm which is very frequently used in 2D, and that's where it gets the name Quadtree, because what it'll do is it'll create it'll split into 4 points, and then it'll do that recursively over and over again. If you had like a plane. Sorry, I was going to sneeze. I didn't.
Okay.
So this has been known for a while, and the analysis for that it gives you a log n approximation where n is the number of points. So note we're already sort of getting that here. We're getting a little bit worse. So the new analysis here really doesn't give you any improvements for that. Actually, sorry, what you get is like actually no, maybe I have to double check that. But like, usually the way you look at that is you have a grid, like a k by k grid, and then the approximation will depend on the log of k. So
right.
Our analysis here doesn't actually improve that, because crucially what we were kind of improving is like the dependence on the dimension. Like before you were getting log n times log d. But here in lower dimensions, we don't this new analysis, like again, like on the slide I said that, like, you know, sort of the new thing that we're trying to say is that like in the old analysis you had log d levels to split early, and at each of them you paid some worst case cost. The issue is the thing that you're stating in the plane is that the worst case cost is there's no extra log n in the worst case cost, because when you cut something, like there's a deterministic bound on how big the grid size is. Like if I impose a grid, the grid is fixed, has a fixed diameter on the plane. But when you go to high dimensions, there is some fixed diameter, but it's way too large, because just because of the way the curse of dimensionality. Basically, you can't use like the side length. If you have a side length of 2, and on the plane, the worst case distance of 2 points is like root 2, or in L1 it's 4. But in the hypercube, if you have side length 2, it's like 2 to the d is the distance the points could be at. Or sorry, not 2 to the d. It increases with the dimension. We're kind of our analysis is really handling this curse of dimensionality type thing. So I guess I don't think that there's anything. We thought for a while whether there's some of these new ideas could be used to solve certain random cases on the plane in improved approximation. We never really fleshed that out too well, but I think in the general case, this won't give you any improvements over what was already known in the plane, theoretically or practically.
Yeah, I mean, I think the part that I really appreciate is this new analysis, right? And I think that piece is, instead of looking at worst case, but looking at sort of the frequency of the worst case. I feel like that idea is really cool. So the last bit I was asking is that you mentioned the minimum spanning tree approximation in high dimension. Is that actually in the same paper, or is it a different paper?
Okay, it's okay. So it's going to be a different paper. But we'll see. We may merge the papers. We haven't decided yet. It depends on how the thing is that they share some analysis, but they're also different in this paper. It might get rather long. So the answer is I don't know yet, but maybe it'll be in the same paper.
All right, so maybe I'll ping you in like, I don't know, 3 to 6 months.
Yeah, the paper with this stuff is online already. The paper with the MST is still being written actually. So yeah. Okay.
All right. Sounds good. Okay.
So happy to answer any questions later on. If you just feel free to email me.
Yeah. All right. Thank you so much. So
okay, if there's
nice to meet you. So if there's no more questions, I'm going to end the recording. I think I made the host, so I'm going to